This is Lean Together 2026, and we're ready for our last talk of the conference by Atticus Kuhn, who's going to be telling us about Buki automata.
Mhm.
Go ahead.
Yes, thank you. Welcome everyone. And today I'm going to be presenting on work I've done in formalizing Bushi automata model checking in Lean. So my name is Atticus, and I'm a student at the University of Cambridge. So here's a brief outline of what I'm going to talk about today. First, I'm going to motivate my discussion. Why am I interested in this question? I'm going to introduce the theory of ranking functions as ranking functions pertain to the domain of formal methods. And I'm going to talk about why I decided to use Lean 4 to formalize this project and and the method I use to formalize this. I'm also going to talk about a new direction which is being explored in the field of model checking, which are neural ranking functions. And finally, I'm going to be talking about a current direction that I'm investigating, which is applying these techniques to combine Lean and neural ranking functions to the area of program termination analysis. And at the end, I'd be happy to discuss any questions that you have. Before I begin, I'd just like to very briefly introduce myself. As I said, my name is Atticus, and I'm a final year computer science student, and I'm an undergrad at Trinity College in Cambridge. So the work I'm presenting today, I did it in collaboration with researchers at the University of Birmingham, and it focused on formalizing techniques in program termination analysis in Lean 4. So specifically, I used the techniques of automata theoretic model checking from the field of formal methods in this work. And in the future, I plan to apply for a PhD in formal methods and programming languages and continue this research. And so I'd like to acknowledge and give thanks to Mirko Giacobbi, Abin Dempel, and Tarka Roy at the University of Birmingham for helping me with this project. Now I'd like to give some motivation and talk about the core problem and why we're interested in it. So on the left, I have a model in Verilog. We start out with a counter c equals 0, and on every clock edge, we increment the counter c equals 0, 1, 2, etc. We have two conditions. The first condition A says that c is less than 60, and the second condition B says that c is equal to 60. On the right, I have a property that I'd like to check in linear temporal logic, or LTL. And this is the formula phi, which is A until B. And this can be read as A holds until B holds, or it can equivalently be read as C is less than 60 until C is equal to 60. Now, you might intuitively be able to see this by inspecting the Verilog, but how would we check it? This brings us to our central model checking question, which is, can we verify that for every run R, which is admitted by our model, can we verify that this run satisfies phi? Or we can ask the converse question. We can ask, is it impossible for us to find a run R that violates phi? And this is what I investigated in this project. I'll just give a bit of background into the theory of formal methods. So this is a question which was tackled by Moishe Vardi in the 1980s. And he used the automata theoretic framework, which is to use the theory of Bushi automata to unify these three questions. Let me go into what they are. So the first is that our linear temporal logic statement, not phi, so we negate our formula, not phi is unsatisfiable. So we translate this from linear temporal logic into a Bushi automata, which is a certain type of automata. And we get that, and so that's equivalent to saying that the product automata of AM cross A not phi is fair empty. And what I mean by fair empty is we define a set of fair states, F. And you can think of a state as being fair if the system does useful work in that state. And so we want every run to visit the fair set a finite number of times, which is what we mean by fair empty, that there are no infinitely fair runs. And then we have another equivalence, which is to say that this is equivalent to saying that the automata A admits a ranking function. And intuitively, I'll get into this a bit more later, but you can intuitively think of a ranking function as being an upper bound on the number of visits to the fair set. Now, why is this a useful framework? Well, here's the key idea of the framework. We've translated a linear temporal logic statement into the truth of the linear temporal logic statement into the existence of a ranking function. So we can prove the linear temporal logic statement holds by constructing the ranking function. And the ranking function serves as a witness of the non-existence of counterexample runs. So we've effectively turned a for all statement, which is for all runs R, into a there exists statement. There exists a ranking function f, and this is useful because we can try and synthesize this ranking function f automatically, which I'll get into later. So this makes the approach amenable to synthesis and verification. Now I'd like to give a bit of definition, a bit more of an explicit definition of what I mean by a ranking function. So a ranking function, you can think of it as being a function R from S to W, where S is our set of automata states and W is a well-founded set. And by well-founded, I just mean that there are no infinite chains of descent. But for this talk, you can just think of W as being either the natural numbers or the ordinals, because the natural numbers are sufficient for proving the termination of a finite program, and the ordinals are sufficient for proving the termination of an infinite program. So remember the fair set that I introduced earlier, which is the set of states where we do useful work. Well, there are two conditions. The first condition is that non-fair transitions are non-increasing, which means that if current is an unfair state and we transition into next, that means that the rank of current must be less than or equal to the rank of, must be bounded by the rank of next. The second condition is that the fair transitions lead to a strict decrease in the ranking function. So if current is a fair state and we have S1 goes to S2, then the rank of S2 must be strictly less than the rank of S1. So why is this a useful definition? Well, if we combine these two conditions with our well-foundedness condition of W, we get the following: that if we would have some infinitely fair run, so a run that visited the fair set an infinite number of times, then that would create an infinite descent of ranks, because each time we visit the fair set, we strictly decrease the rank. But this would contradict our well-foundedness assumption on W, because we assume that W is a well-founded set. Therefore, we conclude that if we had a ranking function, then no such fair run can exist. So I guess I don't have to preach too much to the choir here, but I'm just going to briefly discuss why I decided to choose Lean 4 specifically for this project. I have experience also in AGDA and other theorem provers, but I specifically chose Lean for this project. And the main reasons were, one, the existence of ordinals and well-founded relations were already in MathLib, so I didn't have to define this myself. And also, there's a wealth of automated tactics, including SIMP, Omega, Linearith, that I used for this project. And so this creates some benefits from using Lean. So I was able to create clean proofs by relying on the definitions of well-foundedness and ordinals already in MathLib and on well-founded ranks. And I could also reuse my theorems easily to create modular proofs. So now let me give a concrete example of how ranking functions work and how we can use on the example that I introduced earlier. So here's the example I introduced earlier with the counter, which starts at c equals 0 and increments. And we have our conditions A and B once again. And we have a formula phi asserted in a Verilog language. And here we have translated into automata A, not phi, using the LTL to Bushi automata translation that I talked about earlier. In this diagram, the double circles represent fair states, and the single circles represent unfair states. So we can see we start the initial state in Q0. Now on the bottom, we have a diagram showing the transitions between our states. So the green the green region represents the set of all initial and the set of all reachable states, which are states reachable from the initial conditions. And on the top right, we have each state annotated with its ranking function. So we start with 61, then go to 60, 59, all the way to 0. Now you should notice that there is actually an infinitely fair loop, which is this in red, this infinitely fair loop. But because this infinitely fair loop is outside the set of reachable states, it doesn't affect, it doesn't refute phi. So this ranking function demonstrates that phi holds. Now I'm going to talk about a bit about how I formalize these concepts and these proofs in Lean. So so here are the definitions that I used in Lean. So I define an automata based on its transition relation, its initial set, and its fair set. And I defined a run as merely being a function from the natural numbers to the set of states. So it's so an infinite. So in essence, that would be an infinite sequence of states. Then I defined a natural number ranking function as a function from the states to the natural numbers, satisfying the conditions that are introduced, and an ordinal ranking function as being a function from the states to the ordinals, also satisfying the conditions I introduced earlier. And now here are the two definitions I talked about earlier. So we say a run is fair if um, if it's infinitely fair, if it visits the fair state infinitely often. We can formalize this by saying that for any index n, there exists a greater index k such that k is a fair index. And then we can use that to define an automata as being fair empty, where we say an automata is fair empty if all of its runs are not infinitely fair. Now this brings us into the central theorems, which I formalized. So these are the theorems of Vardy and also some extensions as well. So the first is Vardy's equivalence, which says that so if we have some automaton A, and this theorem works on an infinite or a finite state space. So if we have some Bouchier automata A is fair empty if and only if there exists an ordinal ranking function on A. And then we have this special case, which is if the state space is finite. So if the set of states S is finite, then it's sufficient to only check the natural numbers. So then we can say that A is fair empty if and only if there exists a ranking function on A over the natural numbers. So these are the theorems that I've already introduced in his paper. So now I'd like to just briefly preview how I prove this and the techniques that I use to prove this. So the first direction is the soundness direction, which says if we have a ranking function f, then we conclude that our automaton A is fair empty. So this is the easy direction, and I previewed this a bit earlier, but essentially it states that, well, imagine for the sake of contradiction, we have some infinitely fair run. Here I have our infinitely fair run where the red states are fair states. So we have and let's say they occur at index I1, I2, I3, etc. Then what we can do is we can check their ranks. So the rank of row of I1, the rank of row of I2, rank of row of I3. And we notice that they must strictly decrease by the ranking function condition. So rank of row of I1 must be strictly greater than the rank of row of I2, etc. And this would create an infinitely descending sequence. And whether it's in the naturals or the ordinals, this is impossible because it violates the well-foundedness condition. This is our contradiction, so we conclude that such an infinitely fair run would not exist. So here's an excerpt from my proof in Lean. So we have this sequence, and we use the well-foundedness of the ordinals. Now, the opposite direction of soundness is our completeness direction. So this says, and this is a bit more interesting. So I'd say this is the interesting direction, which says if our automaton is fair empty, then we need to construct an ordinal ranking function on the automaton. And I did this proof in two steps. The first step was to say, if the automaton is fair empty and this succeeds relation is not well-founded, then we'd have a contradiction. But on the other hand, if the succeeds relation is well-founded, then we could construct the ordinal ranking function. Now, what do I mean by this succeeds relation? This is a notion that Vardy introduces. So he introduces the notion of succeeds, where we say that S1 succeeds S2 if there's a path from I, an initial state, to state 1, S1, to a fair state F, and then to S2. So why is this a useful definition? Well, it's a useful definition because imagine we had an infinitely descending chain, S1 succeeds S2, succeeds S3, and so on. We could stitch together the paths from all these succeeds relation to create an infinitely fair run. But since we assume that the automata is fair empty, we have no such fair run. So therefore, we would have to conclude that the succeeds relation is well-founded. So let me go into a bit more detail about why we know the succeeds relation is well-founded. So let's assume that we have this infinite chain of succeeds. So S1 succeeds S2, succeeds S3. So here's the data from S1 succeeds S2, which is I1 and goes to S1, goes to F1, goes to S2. And similarly, the data that we can extract from S2 succeeds S3 is I2 succeeds S2 succeeds F2 succeeds S3. So, and remember the definition of S1 succeeds S2 means that there is some initial state I and some fair state F such that we can go from I to S1 and S1 to F and then F to S2. And we have to make sure that from F to S2, that's at least one step in the path, whereas the other ones is a path of 0 or more steps. And then we can stitch together these segments. So we can stitch together all this data to get a path I goes to S1, goes to F1, goes to S2, goes to F2, goes to S3, goes to F3. So this path, we have an infinitely fair path, which is F1, F2, F3. And this path contradicts the fair emptiness of the automaton, which means that the state succeeds is a well-founded relation. So let me finish the proof of completeness. If we have this well-founded relation succeeds, then we can construct our ranking function. And this relies on theory from the field of ordinal theory, which is where I relied on MATLib. So it's a theory it's known from the theory of ordinals that any well-founded relation induces a function on the ordinals. And here's how we can define it. We can define it as the rank of S over all states S prime, which S prime succeeds S, the rank of S prime plus 1. And why produce a ranking function, a valid ranking function? Well, we have to check the two conditions. The first condition is that S1 steps to S2 and S1 is not fair. Well, then any path to S2 would extend S1. So we'd have the rank of S2 is less than or equal to the rank of S1. On the other hand, if S1 is fair, then we would have that S2 succeeds S1, which implies by our definition that the rank of S2 is strictly less than the rank of S1. And so here's an excerpt from my formalization in Lean, where I use is well-founded.rank, which is already defined in MATLib. Now I'm going to consider a simpler case, which is a finite state space. So if space S is finite, then we can actually simplify the result to say that if the automata is fair empty, then we can construct and then there exists a natural number ranking function. And this is probably what more intuitive. It's you can just count, since the state space is finite, we can just count the number of fair states which are reachable in the future. And that's what this definition captures, that the rank of S, that's the cardinality of the set of S2, such that S can go to S2 and S2 is fair. And why is this a ranking function? Well, the first step is that it's bounded. So we know it's a well-founded, it's well-founded. We also know that it's non-increasing, because if we have a relation S1 steps to S2, then any states which are successors of S2 would also have been reachable from S1. So the fair successors of S2 would also be fair successors of S1. So the rank of S2 would be less than or equal to the rank of S1. And here's the critical part. If S1 is fair, then we can then we can have a strict decrease. And the way I prove this is I said, well, let's assume that the rank of S2 equals the rank of S1. Well, then we would have a cycle, we would have a cycle of fair states, and this would contradict our fair emptiness property. So, which gives us that it decreases. And here's an excerpt from my Lean proof. So I take the cardinality of the set of fair successors of S on A. Now I just have a small toy example. This is the toy example of the Ackermann system. And I created this to show why the ranking function technique is a useful technique for proving the termination of automata systems. So I created this Ackermann system based on how a stacker machine would compute the Ackermann function, where the Ackermann system has a pair NL, where N is the current number and L is the stack of the rest of the number that we're going to compute. And it essentially simulates the computation of the Ackermann function. And so I proved that this system actually cannot be proven terminating using natural number ranking functions alone. It requires ordinal number ranking functions. So as a concrete example, here is one such ordinal ranking function that you could use to prove the termination of the Ackermann system, where omega is an ordinal. And so I essentially uses Cantor normal form of the ordinals using omega. And so I proved that on each step of the Ackermann system, this ranking function strictly decreases, which proves that the Ackermann system halts on all inputs. Now I'm going to go in a slightly different direction and talk about neural ranking functions. So this is a novel direction in the field of formal methods, where instead of writing our ranking functions by hand, the idea of neural ranking functions says, what if we generate a function and then we try to verify whether this generated function actually is a valid ranking function? So here's the definition of a neural ranking function, or NRF, where it consists of activation layers and then a dot product layer. So each of the activation layers, Sn, it consists of a matrix multiplication and a vector addition, followed by our activation function. Then the final layer consists of a dot product of the result with this linear transformation. So you might be thinking, well, this seems rather simple. Can we really represent a complex kind of functions that you might encounter in real-world programs, real-world ranking functions, using this NRF architecture? And the answer is actually yes. So this has been empirically, NRF has been used to verify the termination of programs and verify the correctness of LTL formula. So an example, here's a gadget that can be encoded in neural ranking functions. So imagine if you want to check if X is between A and B. Well, here is a neural ranking function that checks this. So this function is 1 if X is in the interval A, comma B, and it's -1 otherwise. So here's a diagram showing that same gadget. So our activation function, in this case, activation of Z is +1 if Z is greater than 0, and -1 if Z is less than 0. So you can imagine this left neuron, it checks if X is greater than A. This right neuron, you can think of it checks if X is less than B. And this third neuron, it checks if it ANDs them. So in only 3 neurons, we can check if X is between A and B. So here's where my formalization comes into play. So I formalized the NRF completeness theorem, which is a theorem from the recent literature that proves that this architecture is actually expressive. So it says that if we have any function R and over a finite domain, it can be represented by a neural ranking function. So I call this the lookup table approach, where we can check each input and map it basically using a conditional to its output. And here's the basic idea of the proof. So using the gadgets I demonstrated earlier, you can actually create a wide equality gadget. So it checks if the vector x equals vector a for all indices. And then we use AND to check which of these conditions is true. And then we use the dot product to select the final output. And here's my formalization in lean. Now here's you might be thinking, well, that's maybe it's complete, and your ranking functions are complete, but they're not efficient in terms of their count of neurons. Well, actually, I also formalized the efficiency result, which says that piecewise linear functions can be efficiently represented. And by efficiently, I mean with a linear number of neurons by a neural ranking function. So if we have some piecewise linear function f, where f has w conditionals and a conjunctions in each conditional, then we can realize f by a neural ranking function with w 3a plus 2 neurons, so it's linear in both w and a. And the way I formalize this is I represented f as this sum of checks and then linear transformations. So each check is a linear transformation and followed by a comparison. And this is a vector comparison, so it holds if each index is in the range. And then, so if this check holds, then we do the corresponding linear transformation. And if we sum this up, this essentially gives us the piecewise linear function. So let me go through a bit how I prove this. So I built it up with smaller gadgets. So sigma we've seen, and interval and in range. Now I'm going to go a bit into termination analysis. So this is the area I'm currently exploring. So I constructed this simple DSL in Lean using the Lean syntax macros. So each DSL only contains a single while loop, and the loop body consists only of linear assignments and conditionals. And the reason that is interesting is because we can represent the transition function of our automata using a piecewise linear function. So here's an example of a run on this automata. So with the ranking function of 100 minus v0, and you can see that the rank strictly decreases. Now, so here's what I've proven so far. So the blue represents things I've formally verified in Lean. So the program P terminates if and only if the automaton A is fair empty, if and only if we have the ranking function f on A. And here's something I haven't quite done yet, which is to say, given that we have this ranking function A, how many branches are in that ranking function? This is something I don't quite know yet, but I think it's true that we can put an upper bound on the number of branches. So if we have this, then I can say that I have that many, a neural ranking function with that many neurons. And here's why it's important, because the whole point of neural ranking functions is that they can be efficiently generated and verified using integer linear programming solvers. So now I'd like to open the floor for some discussion. So I welcome any questions you have. So here's my email, atticusmkuhn@gmail.com. So, and if you have any further questions or you'd like to talk more about formal verification, I'd be happy to answer your emails. And I'll just briefly recap the main things I talked about. So the first thing is that we can check LCL models using the existence of a ranking function, which serves as our witness. And we can use Lean4 to formalize this entire system. And it works for both finite and infinite state systems. And that this formalization is expressive enough to be extended to modern techniques in the field of formal verification, including neural ranking functions. So thank you for your attention, and I'd be happy to answer any questions.